Good morning, students. This is Mr. B. Just wanted to give you a video to cover the topics we're going to be covering this week in physics. Good news for the Tuesdays and Thursdays of school. Usually I can only meet with you guys on Mondays and Wednesdays due to a conflict I have in my schedule, but we do have a co-teacher who has been gracious enough to help us out with this class. So you will have a teacher to talk to you on Tuesdays and Thursdays to do with material. I will continue to help out on Mondays and Wednesdays as I can until we can get that teacher set up with an account and access to all of your information to get in contact with you. I'm going to make this recording for the physics regular class that's meeting today on Tuesday, September 10th. Okay, so let's get started. We've got a lot to get to today. So I'm going to trust that you guys have read through topic 1, that you have completed the assignments that are contained in topic 1. I didn't get too many emails this week, so remember that if you're lost or if you're not understanding something, the best way to overcome that is to either ask your classmates for help or to email me, okay? I don't mind emails, I really don't, so please email me if you're lost. So today we're going to be in topic 2 in the course. Okay, so if you go to topic 2 on the course, it's called Kinematics. Now I've already clicked on the reading for this topic because I'm going to be referencing this often as we discuss kind of the more difficult points to understand today. But I also have an agenda for items I want to go over. So I went through all the homework for this next week, and I'm going to touch on some concepts that will help you as you attempt those assignments. There will be a lot of math this week in that homework, so just be prepared for that. Have a calculator on hand. Take good notes, especially when it comes to equations and definitions. And realize that in any math question, it's always a good idea to write down your variables that are being given to you and to write down the variables that you don't know yet. That's going to help you pick out the equation that you need. Okay, so first on my agenda is vector quantities. So in topic 2, if you've read it or if you haven't read it, you will be introduced to something called a vector quantity. Okay, simply put, a vector quantity is, I'm going to type this just so you can take notes. A vector quantity is any quantity of measurement that has magnitude and direction associated with it. Okay. Now that definition has 2 things I want to highlight. Magnitude. Okay. Magnitude is just a fancy word for size. Okay. So for example, if my car is driving 65 miles per hour, the magnitude or the size of my speed is 65. Okay. So magnitude is the actual number that you measure when you measure something. Okay. The other component of vectors is direction. Okay. So direction can mean up, direction can mean down, direction can mean at a 45-degree angle. Any information about the measurement that denotes where it's going is a direction. Okay, so once again, vectors are any quantity of measurement that has a magnitude and direction. Okay, so let's talk about some examples of this. Okay, so I'm going to go down to my next bullet point here. So the first thing we're going to talk about in this topic is distance versus displacement. Okay, now you already know what distance means. You've known that forever since you were a little kid. So distance is basically how far something has traveled in a given amount of time. Displacement, however, is a vector quantity. Okay, so distance is the total, let's put it this way, I don't want to use the word distance in the definition for distance. Distance takes the entire path into consideration. Okay, so for example, let's suppose that I was drawing out my path to school. So let's say that this dot represents my house, and let's say that this dot represents my school. Okay. Now, as the crow flies, we could get from point A to point B very quickly if we were in a fast-moving car. But it's probably very unlikely that the path that you take from your house to your school is a straight line path. More than likely, you have to drive several city blocks, or maybe ride a bus, maybe even get on a highway or the freeway. So suppose my path to school looks something like this, okay? So I had to drive maybe 3 blocks east. I had to drive maybe 6 blocks south, and perhaps 9 blocks further to the east. Okay, so the entire path that I drove is 3 blocks plus 6 blocks plus 9 blocks. Okay, so the total distance I drove was 18 blocks. Okay, so that's distance. That's pretty simple. It's just adding up every single part of the path that you took to get from point A to point B. Displacement is a little bit different. So I'm going to erase the drawing, and I'm going to write down a good definition for displacement. So displacement is a vector quantity. And remember, vectors mean that it has a magnitude and direction. Okay, but displacement, it only takes the starting and final positions into account. Okay, so as the crow flies, as they would say, as the crow flies. So suppose for a second we go back to our example where I had to go from my house to school, and I had to drive 18 blocks distance to get there. Okay, so if we're in this scenario again, my distance was 18 blocks, but my displacement is just the straight line distance from where I started to where I finished. Okay, and you can measure that a couple different ways, but basically the easiest way to do this is to make this into a right triangle. Okay, so if I'm trying to figure out what that straight line purple line distance that I drove is, if I make this into a right triangle, you've probably taken geometry before. If you remember Pythagorean theorem, if I know the 2 legs of a right triangle, a squared plus b squared equals c squared, I can sum the squares of those 2 lengths, square root my answer, and I'm going to get the hypotenuse of that triangle. So once again, if I drove 3 blocks east, 6 blocks south, and 9 blocks east again, you can see that my total horizontal distance, my east to west distance that I drove, is 3 plus 9, which gives me 12. Okay, so this horizontal leg of my triangle is 12. Okay, the total vertical, the total north-south distance that I drove was only 6 blocks. Okay, so my other vertical leg is 6. So then I can say, okay, 6 squared plus 12 squared equals c squared. Okay, and then you could solve that thing for c and figure out what your hypotenuse would be. Okay, so your hypotenuse would be c. You would get an answer for c, and bam, you got your straight line distance as the crow flies. Okay, so once again, distance takes the entire path into consideration. Displacement only takes the initial and final positions into account. So whenever you're calculating displacement, you're going to be doing Pythagorean theorem, basically, if you're working in 2 dimensions like this. Now, I want to point something out. Distance and displacement, do not confuse them with each other. You could drive from your house to school and back, and in the previous example, if it was 18 blocks both ways, you drove 18 blocks to get to school and 18 blocks to get home from school, you would have driven 36 blocks total over the course of a day. But displacement, if it only takes the starting and final positions into account, if you drove from your house to school and then back at the end of the day, your initial point was your house. That's the point you started from. Your final point at the end of the day is your house, since you came home. So if that's true, if your initial and final points are the same, your displacement as the crow flies is 0, because at the end of the day, you ended up right where you started. So just keep that in mind. Distance is the total of your path taken, the total distance of the entire path. Displacement is the distance from starting point to finishing point as the crow flies. Okay? All right. Let's go on to our next concept here. We talked about displacement versus distance. Let's talk about a similar comparison. We've got speed versus velocity. Okay, so speed is the distance an object travels divided by the time of travel. Okay, so in the previous example, if I drove 18 blocks to get to school on Tuesday morning, let's say, if I drove 18 blocks and it took me 15 minutes to do it, okay, I could take my distance, 18 blocks, divided by my time, 15 minutes, and I would get my speed that I just drove, okay? So I'm going to do that real quick. 18 blocks divided by 15 minutes. That means I'm traveling at a rate of about 1.2 blocks every minute. Okay, 1.2 blocks per minute. Okay. Now remember, we're using the 18 blocks because this is the distance we took. It's the entire path that we took to get from point A to point B. Okay. As far as velocity is concerned, velocity is the displacement an object travels divided by time. Okay, so remember that in the previous example I gave, if I wanted to take the distance as the crow flies, I'd have to do Pythagorean theorem to figure out what that straight line as the crow flies distance was. Okay, so in that case, I would put that distance over 15 minutes, and that would give me my velocity. Okay, even more interesting though, consider the scenario where you're returning home at the end of the night and you want to figure out your velocity for the entire day. So if my displacement from start to finish, if I'm starting at my home and I'm ending at my home at the end of the night, my displacement is 0. Okay, now imagine what that does to your velocity. If I have a displacement of 0, okay, let me switch colors here. If I have a displacement of 0 blocks, since I returned home, right back where I started, and how long is school? I mean, because I need to take my total time of the problem. So your typical school day lasts maybe 8 hours. It took you 15 minutes to get to school, maybe 15 minutes to get back. That's 8.5 hours. Okay, but you can probably see that our displacement being 0, 0 divided by anything is 0. Okay, so even though I traveled to school in a car that goes decently fast, because my displacement is 0, I ended up right where I started. Technically, my velocity would be 0 blocks per hour. Okay, that's kind of depressing because you did all that work to get to school. You drove in a very fast car to get back. And yet, because you ended up where you started, your displacement is 0, and therefore your velocity is also 0. So keep in mind that velocity can be misleading if you don't know the whole story. Okay, speed is a little bit more revealing about what's actually going on in your life, because it takes the entire path into account. Okay, now I don't want you guys to be harsh about velocity being as vague as it is, because displacement and velocity, these vector quantities we're going to use, they are going to be very useful to us in solving problems. Okay, and we're going to get to some example problems at the end. So if you're kind of confused about how this relates to the homework, stay tuned, we're going to get there. Okay, my next bullet on the agenda, on the homework, you're going to see a lot of problems referring to average speed or velocity versus instantaneous speed or velocity. Okay, so I'm going to give you kind of an example. Okay, so suppose, let's talk about average speed, velocity first. Okay, so if I wanted to figure out like my average speed or velocity, I don't want to make you guys confused. So I'm just put in parentheses or velocity. If I want to figure my average speed, I'm going to take my final speed minus my initial speed, okay? And I'm going to take that difference and divide it by my total time. Okay, what's my time, okay? So, for example, if I was traveling on the freeway and I was going 65 miles an hour, and then suddenly there was construction on the freeway and I had to slow down to about 45 miles per hour, okay? In that case, my final speed would be 45 miles per hour. I started driving at 65 miles per hour before I hit construction. And suppose that I was on the freeway for about 30 minutes, maybe going home from school. Okay, 30 minutes. All right. If in that case, your final, you know what, I'm realizing that I'm getting a little ahead of myself. I'm describing acceleration right now. Let me kind of go back a little bit. Your average speed or velocity is not your final speed minus your initial speed. It's your final position minus your initial position. Okay, that's going to be a little bit better. Sorry about that. I was describing acceleration, but I was using the words for velocity. Okay, so for example, if I'm starting at my home and I'm going to school, okay, suppose that my school is 18 miles away, my final position would be 18 miles away. If I was starting from my home, which is point 0, okay, my final position minus my initial position would be 18 miles that I've driven minus 0 miles that I had driven to start with. Divide that by the total time. Let's say it took me 30 minutes to go 18 miles. Okay, 30 minutes. And up here we have miles. I could plug those numbers in. 18 minus 0 divided by 30, and I would get about 0.6 miles per minute. 0.6 miles per minute. Now realize that doesn't tell me much about my journey. That's just an average. For all we know, I could have run into construction on the way to school. So was I really driving 0.6 miles every minute the entire way? No. I could have run into traffic. I could have sped up a little bit after that traffic to get to school on time. So the average is just your final minus your initial over your time. Okay. Let's talk about instantaneous though. Okay, because remember this little bullet point we're covering right now is talking about, hey, what's the difference between average speed or velocity versus instantaneous speed or velocity? So instantaneous speed / velocity is how fast an object is traveling at that particular instant in time. Okay, so if your average speed for the entire journey to school was 0.6 miles per minute, well, how would you figure out your instantaneous speed? Your speed at that very second? Well, you'd probably look at your speedometer on your car. Okay, and your speedometer would say something like, oh, you're driving 60 miles an hour right now. Okay, so instantaneous, you can look at a speedometer to figure out how fast you're going at that instant in time. Average speed or velocity is just your final minus your initial divided by the time it took. Okay. Okay, and there'll be some questions in the homework about that. Okay, let's talk about these terms right here. And this is kind of where I have to apologize. A few minutes ago, I started mixing things up. Hopefully, I was able to recover a nice enough for you to grasp the concept. But there's basically 3 terms in this chapter that you need to be able to distinguish from each other. You've got displacement versus velocity versus acceleration. So remember, displacement is the start to finish distance something has traveled as the crow flies. Velocity is that displacement over time. And then shortly we're going to talk about acceleration. Okay? So I'm going to set these up in a series of equations. Okay? So usually in textbooks, displacement is represented by the variable x. Okay? So the variable for displacement is usually x in most textbooks. The variable for velocity is usually v. Okay? And, you know, pretty obvious, variable for acceleration is usually a. Okay? So, displacement, there's not really an equation for it because you can just measure it. Either using, you know, a tape measure if it's a very straightforward distance an object is traveling. You can use Pythagorean theorem if you're trying to figure out an as the crow flies distance that something travels. But displacement is just the as the crow flies distance that something's traveling. If you want to figure out velocity, you're going to do that using the equation I just showed you up above. Okay, so this equation, I'm going to put it into variables right now, just kind of give you another way to look at it. Okay, so displacement, let's say I was trying to figure out velocity. Okay, velocity is my final displacement, my final position, I should say, minus my initial position divided by time, kind of like what we saw in the school example. Okay, so in the school example, x sub f, my final position was 18 miles. So that's how far away my school was. My x sub I, my initial position was position 0 because that's where I started. So 18 minus 0 gave us 18. And if that took me a time of 30 minutes, which I plug in for t, that's kind of where we got our answer from in the previous example. So that's an equation you need to know. Put a star next to it. This is for average velocity, x sub f minus x sub I over t. If I wanted to figure out what acceleration was, it's going to be a very similar equation. Now, before you get into the equation, think about what you know about acceleration. Acceleration is basically how much you are speeding up by over a certain amount of time. So you might have heard car commercials say that this car accelerates from 0 to 60 in 4 seconds or something like that. Okay. Acceleration is equal to your final velocity minus your initial velocity divided by the time it took. Okay. So let's take that car commercial that you probably heard on the TV, and let's analyze it for a second. So let's say that a new car is on the market, and it can accelerate from 0 miles per hour to 60 miles per hour in 4 seconds, let's say. Okay. So if I'm accelerating from 0 to 0 to 60 miles per hour in 4 seconds, my final velocity would be 60 miles per hour, since that's what I'm accelerating to. My initial velocity, well, I just told you we're going from 0 to 60, so my initial is 0 miles per hour. And if that was in 4 seconds, okay, I plug that in for my time. Okay, so I've got my units up top were in miles per hour. My unit on the bottom was in seconds. And one thing I should mention is time is important to make sure that you're in the same unit. Okay, so what you see here is that I've got differing units of time. I've got miles per hour on top, but I've only got seconds on the bottom. Okay, so you would need to fix that in order to go further with this problem. Okay, so keep in mind that in an hour there's 60 minutes, and in every minute there's 60 seconds. So in 1 hour, I've got 60 minutes. Okay, so my hours will cancel. And then in every 1 minute, I've got 60 seconds. Okay, so basically my minutes are going to cancel. So my total seconds is just going to be 60 times 60. Okay, where 60 times 60 is 3,600. Okay, so really my miles per hour should be 60 minus 0 miles for every 3,600 seconds. Okay, and then my seconds are now agreeing with each other, and so they will cancel when I do this problem. Okay, so just be careful, and we're going to get more into this when we actually start doing more problems. But in cases like this, where our time unit didn't agree with itself, we had minutes on the top, or excuse me, hours on the top, and we had seconds on the bottom. We have to change it so that our seconds agree with each other. Okay. Anyway, I'm kind of digressing, but main thing I want you to know these two equations by heart. Okay. The top one is for average velocity. The bottom one is for average acceleration. Okay. More will come on that when we get to homework problems. Okay. Let's talk about the next thing. So we described displacement, velocity, and acceleration for you. Now let's talk to you about different problems that you could be faced with on the homework. What you see in front of you right here, this table of equations, you are going to be responsible for being able to use this table to solve any problem that's given to you in this topic. Okay? So rather than go through each equation in detail, which you can do on your own if you'd like, what I like to do whenever I'm solving physics problems, I like to have this list of equations by me when I'm doing my work, so I can always look at them. Okay. Now, rather than be so concerned about using the right equation that I just intimidate myself, what I like to do is I like to define all my variables that are given to me in a particular problem, define the variable that's being asked of me, and then pick the equation that's going to get me there. Okay, so I'm not going to expect you to like memorize these equations. You can have them on hand when you're in tests and quizzes, things like that. But just be comfortable using them. So let's define these variables for a second, okay? In this first equation, we have the variables x sub 0, okay? X sub 0, I'm going to call x naught from now on, okay? So whenever you see a subscript of 0, say the word not. Okay, so with x, we've got x naught, we've got v with a little line over it, and we've got t. So let's define those things real quick. Okay, so x is equal to final position. Okay, x naught, I'm going to have to draw a little knot here. X naught is going to be equal to my initial position. Okay. All right. V with a little line over it, I'll draw the line in a second, is your average velocity. Okay. So that's what V with a line over it means. And T is going to be equal to time. So T stands for time. All right. We keep going down the list of equations. Other variables we haven't really talked about yet. We've got plain old V. We've got V naught. Okay, so look for patterns in physics. Just like X was final position and X naught was initial position, V is going to be final velocity, and V naught is going to be initial velocity. Okay, so V naught is initial velocity. Okay, looking down even further, you see the next equation, V is equal to V naught plus AT. Okay, V we said was final velocity. Oh, and by the way, up top in the equation above that, we see V with a line over it. So just like oh, we already explained what that was. Okay, so we're good to go. We see in the third equation down, we introduced variable A, which we already told you was acceleration. Okay, and I think that takes care of it. We define every single variable that appears on this list of equations. Okay, so once again, don't be super stressed about worrying about knowing each of these equations by heart. I'll let you have them on hand when you do your assignments and when you do your tests and quizzes. But in any problem, write down the variables that are being given to you, write down the variable that's being asked of you, and then pick the equation that's going to get you there. Okay? So let's do an example. Okay, so I'm going to switch over to the book. An example. Okay, so these equations are introduced in section 2.5 in your book. So let's suppose that I was doing number 22. Okay, so number 22 reads, a bullet in a gun is accelerated from the firing chamber to the end of the barrel at an average rate of 6.20 times 10 to the 5th meters per second squared. Okay, for 8.10 times 10 to the negative 4th seconds. What is its muzzle velocity? That is its final velocity. Okay, so there's a couple of things we need to do here to kind of take stock of the information that's been given to us. So if I was labeling what I know in the problem so far, I know that my time is 8.10 times 10 to the negative 4th, because that's what they told me the total seconds was. Remember, you're going to do this for every problem. Start by defining your variables. Oops. Sloppy this morning. Forgot to put my 10 in there. 8.10 times 10 to the negative 4th seconds. Okay. So that can be checked off. I've defined my time. Take a look at the other thing I underlined here. It was accelerated from the firing chamber at a rate of 6.20 times 10 to the 5th. So because they used the word accelerated there, this number right here that they gave me, this is my acceleration. Okay, so let's write that down. So my acceleration is equal to 6.20 times 10 to the 5th. Okay. Meters per second squared. Meters per second squared. All right. Now, they're asking me what is the muzzle velocity that is its final velocity. So they're asking us for V. That's what we don't know. Okay. Now, even though they didn't explicitly state it, we need to be worried about what the initial velocity was. What's our V naught in this case? Okay. Well, think about it. V naught stands for initial velocity. In other words, what's the velocity at the beginning of the problem? If a bullet is sitting in a gun at the beginning of the problem, it's not really moving at all. So our initial velocity at the beginning of the problem is 0 meters per second because this bullet is being accelerated from rest. Now, they didn't say that in the problem, but you need to be able to infer that to know which equations you need to use. Okay, so take a look at what we know so far. We know what T is, we know what A is, we know what B naught is, we're looking for what V is. Okay, so I'm going to look at my list of equations on my Word document, and I'm looking for the equation that incorporates all of those variables. Okay, and you'll notice the equation that incorporates all of those variables in it is this one right here. Okay, and look, hey, it's even solved for what we're looking for. So we can just basically plug in what V naught is, we can plug in what A is, we can plug in what T is. Okay, so I'm going to grab that equation, I'm going to bring it over to our workspace here. Okay, so remember our equation that we just saw on that chart was V is equal to V naught plus AT. Okay. And now you're going to get your calculator out. You're going to plug in each of those values where they go in the equation. And you're going to do the math to figure out what V is. Okay. The good news is that V was already solved for, so we didn't really need to do algebra here to get V isolated. So I'm going to pull my calculator. And let's do this on there. Okay. So let me switch to scientific calculator just so I have more functions available to me. Okay, I'm going to move all this stuff up so we can see a little bit better. I'm sorry for the yellow text. It's probably hard on your eyes right now. Next time I'll need to remember to use the darker text on the calculator. Okay, but focus on the orange part for now, that equation. So I'm going to type in V naught plus A times T. Okay, my V naught was 0. So 0. I'm going to add to that plus my acceleration was 6.20 times 10 to the 5th. I'm going to put that in parentheses because it's a scientific notation number. And I'm going to times 10 to the 5th. So times 10 to the 5th, close parentheses. And my equation, I'm timesing A by T. So I'm going to hit times. And I'm going to put my time value in here now, which was 8.10 times 10 to the negative 4th. close parentheses. And I hit equals. And there you have it. We have our value for our final velocity. Okay? So I'm going to say my velocity is equal to 502.2 meters per second. Okay? Let's ask ourselves if that makes sense in the context of the problem. Remember that we're accelerating a bullet from rest in this problem. So is it reasonable that the bullet started out going 0 meters per second at rest, and that this gun was able to accelerate it such that it's now going 502.2 meters per second? Okay, that's a pretty big number, but this is a pretty fast bullet. And bullets travel pretty fast, so that's pretty reasonable. Okay, so just kind of sum it up. We defined our variables in the problem. We looked at our list of equations. We identified the equation that incorporated everything we already knew, as well as what we wanted to find out. And that's how we knew that was the equation we needed. Okay. Now, we're kind of running out of time. And I'll probably end up making another video to go more into depth of some of these concepts. But just to kind of finish up today's session, the last thing I want to talk about is units real quick. So if you're new to physics, you may not be familiar with how we express accelerations or how we express velocity. So let me just kind of give you a quick note on that. I'm going to add on to what we set up here when we were kind of defining what these variables were. So we said that the variable for displacement is usually x. We measure displacement in meters, usually. Okay. Displacement could be measured in feet. That's also a distance. It could be measured in yards. But in this class, we're mostly going to measure displacement in meters. Okay. So whenever you see m in a problem, it stands for meters. Velocity is measured in meters per second. Okay, so whenever you see m/s, that's your meters per second. That's how you know that that's velocity. And lastly, acceleration. This is kind of the weird one. It's measured in meters per second squared. Okay, so whenever you see m/s squared, that's your hint that that's an acceleration they're giving you. And this is important because if you look at the problem we were just doing, in the problem, even though they said the word accelerated up here, another way that I can know that this value they gave me down here was acceleration is because I see that meters per second squared right there. So I'm thinking to myself already, okay, that's the unit for acceleration. So paying attention to the units can help you know what the numbers are that they're giving you. That's going to help you pick the right equation. Okay. Okay, we've got about 2 minutes left before our time is up today. And like I said, I'm going to make another video to cover the concepts that we didn't quite get to in this session. But real quick, before we go, let's at least touch on this last bullet point on my agenda. Being able to examine graphs in this class is very important. You'll see in front of you right here, we've got 3 graphs. We've got a position versus time graph, a velocity versus time graph, and acceleration versus time graph. Okay, so you can see your x-axis in all 3 of these graphs is always time. Okay, so time is always on the x-axis. Okay, yeah, you can see time down there. The y-axis for the first graph is position. Y-axis for the second graph is velocity. For the third graph is acceleration. So I want to talk to you about how these relate to each other. We already told you that velocity is basically how an object's position is changing over time. So take a look at the first graph. I want you to notice something. At the top of the graph, the very peak right here, before this point, the position is going up. After this point, the position is going down. Okay. Now, there's an important concept, two important concepts I want you to pay attention to here. Remember that in Algebra 1, we had y equals mx plus b. M was our slope. Okay. Slope on a position versus time graph is the instantaneous velocity. Okay. So, for example, you can see that this object, whatever it is, as it's being launched upward, okay, it's got a slope that's very sharply increasing, okay? And that slope for this straight line segment right here at the very beginning, it's going up about 6 meters in about half a second, okay? It's going up 6 meters in half of a second. 6 divided by 0.5, in other words, gives you 12. Okay, so this little straight line segment right here, if you were to calculate the slope of that, your slope would be about 12. Okay. Now, if you go down to the velocity graph, since we said that slope is the same thing as instantaneous velocity, you'll notice the velocity starts up here at about 12-ish. Okay. So just keep that in mind. Whenever you're looking at slope on a position versus time graph, slope, if you calculate it, that's the same thing as the instantaneous velocity at that point in time. Okay. So you can see that as this object travels, it starts by with a very high velocity, but then you'll start to see the slope kind of taper a little bit until it finally reaches the peak of this curve. So the slope, it's getting less steep and less steep and less steep and less steep until it reaches the highest point on this graph. Okay, so because the slope is getting less and less steep, that means our velocity is getting lesser and lesser. You can see that this velocity is going down and down and down. Okay, so just be aware of that. Now, after the object reaches this peak on the position versus time graph, then it starts to go down. Okay, so you can see the slope is now going down, and as it gets further and further along this graph, it starts to become more steep in how it's going down. So you can see that reflected in the velocity versus time graph, that now that the object has a negative slope, our velocity is now entering negative territory, okay? Because it's got a negative slope up above. And you can see that as time marches on, this red line gets steeper and steeper and steeper. And this velocity graph, this green line, is getting more and more and more negative, okay? Okay, now remember, displacement and velocity are vector quantities, meaning that they have magnitudes and they have direction, okay? So we just made a big deal of the slope being the instantaneous velocities. We've been talking a lot about magnitude so far, how big the velocity is. Direction is also important. So up above, our velocity was, our position was positive because it was going up on the graph. In the second half of the graph, it was going down. Okay. Similarly, up down here in the velocity graph, the velocity in this segment was positive. In this segment, the velocity is negative. Okay. And lastly, the same kind of holds true for the acceleration graph. So kind of the same thing we talked about above. M for the slope for the velocity graph is acceleration. Okay, so if you take a look at the slope of this velocity graph right here, this straight line, it's got a slope that's going down. Well, let's see here, between the first 2 points, it was at about 12 or 13 up here. When 1 second passes by, it's at about 4 on the velocity axis. So if we're going down from 13 to 4 in the space of 1 second, okay, we're going down by about 9 meters per second for every second that goes by. Okay, so in other words, my slope, if you were to calculate this using like Algebra 1 techniques, you probably get a slope of about -9. Okay, and if you look down at the acceleration graph, lo and behold, my acceleration is about -9. Okay, now it's actually -10 because I'm kind of ballparking here, but you can see that the slope that we calculated up here is very, very close to the actual value of the acceleration down here. Okay, now what we just went over is kind of a tricky concept with slopes and figuring out how they fit into everything. Okay, so just keep that in mind, and we'll talk more about it later. All right, that's enough for today. More videos will be coming to help you with these topics. Get started on the homework early. Good luck. Let me know if you need anything, and we'll see you next time.